Hi friends, now we are going to see discrete mathematics. So here discrete mathematics, first we are going to see what is discrete mathematics. There are two things. One is called discrete mathematics, which is finite and countable, which we can say discrete mathematics. So if it is uncountable, then it is something continuous. Okay, here discrete means we can find it's countable. Countable, finite or infinite, both will be discrete mathematics only. Here there are some operations. First operation is belongs to, and this is about the element we are using, belongs to symbol. So this is for every. If you put a V cross, no, that is for every, or inverted A. This is this symbol we can talk about implies, and these two are such that or there exists. Now first we are going to see the operations, binary operation. That is the first definition we are going to see that. What do you mean by binary operations? So normally we have some operations, plus, minus, addition, subtraction, multiplication, division and all. Some operations are there. Whether these operations are binary or not, that we have to check. So binary operations, if you depends upon the set, natural number, correct? If you take two natural numbers, there are two natural numbers are there, 1 and 2. If you add 1 plus 2, again it is a natural number, correct? So that is called addition. Addition belongs to natural number. Similarly, when you multiply 1 into 2, again this also answer 2, again product also a natural number. So if you take two natural number, if you add, again it is a natural number. If you multiply, again it is a natural number. So it is called binary operation over addition with the natural number. Similarly, we can see about integer. Instead of addition multiplication, we can go with the subtraction, division. Whether it is binary number or not, that we have to check. So first we have to see the, suppose you have 1 minus 2. 1 and 2 are natural number, but 1 minus 2 is not a natural number. So a minus b, a and b are natural number, but a minus b is not a natural number because 1 minus 2 is minus 1. So which is not binary operation over subtraction. Now what is the definition for binary operation? Any operation, star means any addition, subtraction, multiplication, anything we can say that operation means star. Generally we are name it star. Star may be any operation defined on a non-empty subset. Okay, non-empty set of S is called binary operation. It means, so number one, that should be a comma b should be a ordered pairs. Okay, unique, that assignment unique, a comma b, it should be belongs to R. So the operation must be defined such that every ordered pair is S in the set S cross S. It assign a unique element a star b. Okay, a operation with the b should be every ordered pair a comma b belongs to S cross S. So it should be defined in that set. Now let's see closed property. What do you mean by closed property? A star b is always lie in that set. Okay, that is called closed property. So when you take operation, should be lies inside the set. Okay, let's see some example. Minus is not a binary operation on n. I already said minus is not a operation on natural number because when you take two ordered per 3 comma 4, 3 and 4 is ordered per in natural number n cross n. Whereas if you take 3 minus 4, it becomes minus 1. Minus 1 is not a natural number, it is an integer. So minus is not a binary operation on n. Whereas minus is a binary operation on integer, Z. In Z, addition, multiplication, subtraction are the binary operation. Whereas division is not a binary operation in integer. So like that, so binary operation, you have to take two elements in the set. That operation also belongs to the set. So division is not a binary operation in integer. Similarly, rational numbers. When you take q, q is a rational number. In the q, except 0. If you take 0, then it become problem. Anything by 0 become infinity. So 0 except 0, it is a binary operation in the rational number. Similarly, we can go with this is the table. This table will talk about entire number system, whether it is binary or not. Now we take first addition is binary in natural number. If we take two numbers, 1 plus 2, again it is a natural number, but 1 minus 2 is not a natural number. 1 into 2 is a natural number. 1 divided by 2 is not a natural number, so it is not a binary operation. Divide is not a binary operation over natural number. Integer, you take two integer number. So when you take two integer, suppose you take minus 1, minus 2. When you add or subtract, okay, minus 1, minus 2, when you add or subtract, again it is a integer only. When you multiply, again it is a integer. So integer, addition is a integer, subtraction is a integer, multiplication is a integer, whereas division is not an integer. If you take minus 1 divided by 2, it is not an integer. So it is not binary operation. Like that, if you take rational numbers. In the rational number, this is 1 by 2 is a rational number and 1 by 3 is a rational number. If you add, it is a rational number. If you subtract 1 by 2 minus 1 by 3, subtraction of rational number is a rational number. Multiplication of rational number, 1 by 2 into 1 by 3. Multiplication of rational number is a rational number. Division of rational number is not a rational number. How, sir? 1 by 2 is a rational number, divided by 0 is a rational number, but anything divided by 0, it becomes infinity. So it indicates that irrational number, division is not a binary operation. Now real number. When you take a real number, again the same thing. What is real number? Rational, irrational, everything is a real number. So first, if you take irrational number into irrational number, it is a real number. Actually, a product of irrational number is a real number. Subtraction of, okay, real number is a real number. Product of real number is a real number. But division is not a real number, because when you take root 2 divided by 0, it is not a real number. This goes to infinity. Now complex number. When you talk about complex number, you know that x square plus 1 equal to 0, which means x square equal to minus 1, x equal to plus or minus I. So we have complex number system. So addition of complex number is a complex number. A plus IB is one complex number. C plus ID is a complex number. If we add, again we can get complex number. So addition of complex number is a complex number, so it is a binary operation. Subtraction of complex number is a complex number. Product of complex number is a complex number. But division need not be a complex number, because division, you take some number a plus ib, but divided by 0. 0 also a complex number. It becomes infinity. So we can't say that division of complex number is not a complex number. So it is not binary. Except 0. If you remove the 0 from rational, real and complex number, again division is a binary operation, except 0. Understand? Whereas if you remove the 0, it is not binary. It is not binary. It is not subtraction is not binary. Now come to example 1, 12.1. We have to check the closure property. So now we have to discuss. Here simply discussing is enough to tell about examining the binary operation closure property of the following operation on the respective sets. So now A star B, that operation is defined by, you have to add A plus 3 times A into B minus 5 times B square for all real, all integers. You take A, B, B any integer. If you do this operation, again it becomes integer only. So it is very clear. A is integer, A into B is integer, sum of A plus 3AB is integer, B square is integer, minus 5 into B square is integer. So the entire term is the integer. It's very, very simple. So all the terms, when you take all the terms, A, 3 times AB, or 5 times b square, everything is integer. So entire operation is integer. Therefore, it is binary operation. Then when you come to this, we are taking rational numbers. So now a star b is defined by a minus 1, b minus 1. Is it a closure property? No, sir, it is not closure property. Why, sir? Why no? B. For b, if you put 1, what will happen here? B become 1 means 1 minus 1 becomes 0. So it become a minus 1 by 0, which is not a rational number. So it is not a closure property, because if you put b equal to 1, 1 is also a rational number. If you put b value 1, denominator becomes 0. So it is not a binary operation when you put b equal to 1. Some of the properties. So commutative properties. What do you mean by commutative property? A star b equal to b star a. That is commutative property. So it is over addition means a plus b equal to b plus a. We are writing like that. Multiplication, a into b equal to b into a. So addition is commutative, multiplication is commutative. Like that, the star is any operation, any binary operation. It's a commutative property. Associative property. When you take 3 non-empty set a star, b star, c. So first operate b star c, then operate with a, or first operate a b, then c. Okay, associative property. Over addition, a plus b plus c. First you can add b plus c, then you can add a, or first you can add a plus b, then you can add c. Both will give same answer only, no? Like that multiplication. First you can multiply b into c, then finally you can multiply with a, or first you can multiply a into b, finally with the c. Both will give same answer. So here addition and multiplication are the associative property. Whereas division, subtraction not satisfied associative property. Identity element. So normally identity, if you add addition, additive identity, if you add a plus 0 equal to a, 0 plus a also a, so 0 is called additive identity, because when you add with 0, same element will come. Like that, E is the indicator for the identity element. For additive identity 0, if you take multiplicative identity, a into 1 equal to a, or 1 into a equal to a, so 1 is called multiplicative identity. Okay, so like that, E is the identity element. E is the identity element. A star E equal to a, E star a also equal to a. Then E is called a identity element. Then inverse. So if you take inverse, you have to get identity. Suppose for a, minus a is the inverse. You are getting 0 is identity. Okay, so minus a is the additive inverse. Multiplicative inverse means a 1 by a, which is give 1. So 1 by a is the multiplicative inverse. However, inverse we can define with the operation, we have to give identity element. If you do inverse, if you operate with inverse, a minus a equal to 0, or minus a plus a equal to 0. Here 1 by a into a equal to 1. This is multiplicative inverse, this is additive inverse. So in general, a star b equal to e, or b star a equal to e, then b is nothing but the inverse of e. So I already said multiplicative identity, multiplicative inverse. Uniqueness of the identity. So for a algebraic structure, there should be only one identity in that set. There should not be two identity. That is a very important theorem. Uniqueness inverse. So for algebraic structure, there should be only one inverse. Okay, it should be unique inverse, unique identity. We can't get more. For one set, two identity not possible. For one element, more than one inverse not possible. So these are the important result. Now take example 2. So now closure property. Verify the closure property, commutative property, associative property, identity, inverse on addition, integer addition. So integer addition, if you take two integer number, if you add become integer, so it is closure property is true. Commutative, m plus n equal to n plus m, so commutative property is satisfied. Associative, if take n, m, n, p, so m plus n plus p m plus n plus p, so associative property also satisfied. Identity, 0 is the identity element, and when you talk about the inverse, minus m is the inverse. So we can verify all the 5 properties in the addition over integer. Example 12.3. Now subtraction. In the integer, subtraction also closure property. If we take 2 element, subtract, again we can get integer only. Okay, minus is not a binary on natural number, but it is integer. In integer it is set. You take any 2 integer, subtraction of 2 integer is again a integer. Correct? Subtraction of any 2 integer is again a integer. A comma b belongs to integer. It means a minus b also a integer. So closure property is true. Commutative is not true, because when you take a minus b is not equal to b minus a. Okay, m minus n is not equal to n minus m. So not commutative. They ask you to verify. So integer operation is not commutative. Similarly, it is not associative. You take 2, 3 elements. For example, 4, 5, 7. So now we are subtracting 4 minus 5 minus 7, which is not equal to 4 minus 5 minus 7. Both will give different values. Here 4 minus 5 is minus 1 minus 7. Here if we take 4 minus 5 minus 7 is minus 2. So definitely we'll get different answer. Here we get minus 8. Here we get minus 1 minus plus. So this is 6. So associative over subtraction is not associative. It is not associative over subtraction. Now identity. Identity is there. 0 is the identity. When you take 0, 0 is the identity, and inverse, minus is the inverse. So both are identity does not exceed y, they asked, but identity is there over subtraction. They asked subtraction. For addition, additive identity is there. 0 is the additive identity. And so now you have to check. Suppose 0 is additive identity, take 2 minus 0, but 0 minus 2. Both are not equal, no? So subtraction, in subtraction, identity does not exist. Similarly, inverse. Suppose you take 2 minus, okay, minus, if you take minus 2 or minus 2, minus 2. So both are not equal. So clearly inverse also not exists. But for addition it is exists. If you take addition, 2 plus 0 equal to 0 plus 2 equal to 2. So 0 is additive identity, whereas 0 is not a subtraction identity. Similarly, if you take minus 2, minus 2 is the additive inverse. Okay, whereas minus 2 is not a subtraction inverse. So for subtraction over integer, there is no identity, there is no inverse. Understand? Verify closure property over addition is that set of all even integer. Take only even integer, okay, and you have to check with addition. So sum of even number is again even number only, no? So if you take any even number, add, again it become even number. So take 2m, 2n are the two even number. If you add, again you can get 2 into m plus n. So it indicates that sum of even number is again a even number. So closure property is true. Commutative also true. Okay, x plus y equal to y plus x. Okay, so commutative true. Associative also true. Sum of 3 even number is again. And identity. When you talk about identity, 0 is the additive identity for even number, even for even number. And inverse also exists. If you take even number x equal to 2k, so minus 2k is your inverse. That's why inverse also exists. set of all even number. Whereas if you take set of all odd number, it is not like that. If you take set of all odd number, sum of odd number is not a odd number. Sum of even number is even number, but sum of odd number is become even number. So closure property, okay, not a binary operation. We can't get a closure property because sum of odd number become even number. Even number is not the element of odd number set, so it is not a closure. Closure is wrong. Commutative is true only. By adding odd number a plus b, x plus y equal to y plus so. Commutative okay, associative also true. Identity. 0 is the identity. Inverse also true. Closure only we can't get closure. Other things and all okay. We can get. Now verify the closure property. Here a power b defined by a power b. Set of all number in natural number. A power b. So a and b are natural number. If you take a power b is also a natural number. So closure property is true. And commutative is not true. Does not commutative. Because if you take two elements, 2 power 3 is not equal to 3 power 2. Or we can say that a comma b is not equal to b comma a. Okay. Both commutative is wrong. So not commutative. Here a power b is not commutative. Associative. That we have to check whether it is associative or not. Okay. First we are taking b power. So now take some counter example. It is easy for you to understand. 2, 3, 4. Okay. If you take 2, 3, 4, first you can get 3, 4. 3 to the power, 2 to the power, 3 to the power 4. So 3 to the power 4 is 81, 2 power 81. Here a power b, again whole power c. A power b is what? So that is 2 power 3. You can write 2 power 3, whole power what? Whole power 4. It become 2 power 12. So now here we have different values. 2 power 81. 2 power 12. So associative is not true here for a power p. A power p associative is not true. Commutative is not true. Closure property, that is true. That's all. We can go with the next example. So here new operation. This operation defined first addition and subtraction. Product of subtraction. So it is talk about only integer. If you take integer, sum of number also integer, product of a number also integer, difference of the set also integer. So binary operation over. This operation is again integer. So it is closure. Property is closure. Because m belongs to integer, n belongs to integer, m plus n belongs to integer, mn is also a integer, and m plus n minus mn, this also a integer. Therefore m comma n for all is a integer. Therefore it is a binary operation on n. Then talk about commutative. Yes sir, it is commutative only. When you take m star n, m plus n minus mn, we can take n cross m also the same only, because addition we can write m plus n or n plus m. Product mn or nm, everything is same only. So mn equal to nm, therefore commutative is true. Associative. Associative also true. We have to check three terms. Mn, first operation mn, then with the p, we can get this answer. Then first np, apply np, again with the m. Compare these two answers, it is associative. This operation is associative. And identity. For identity, we have to do that operation. What is that? How to find identity? So now put E. So when you take E with the m star n equal to m plus n minus mn. This is your operation. Now as per the formula, we have to go with m star E is equal to again E. So m plus E minus m into E equal to what? M. As per the formula, m star E equal to m. Now take E common. So here 1 minus m in the bracket minus this m get cancelled. M get cancelled. So what is your E? E is also equal to 0. E equal to 0. If you put M equal to 1, it become problem. M is an arbitrary integer, hence need not be equal to 1. So when you take E equal to 0, that is your identity. If you put 0, you can get M again. Then we are going to think about inverse. How to find inverse? As for the formula, so we have to find inverse. So M star n equal to M plus n minus Mn. If we take n is the inverse, then identity. What is your identity? 0 is the identity. So now we have to find what is n value. Take n common, 1 minus m is a common. Here E value is 0, correct? So bring this m to right hand side, become minus m. So n equal to minus m by 1 minus m. This is your inverse. So this is also a whether it is integer or not, that you have to check, because it is in division. So division of some number, no, this is somewhat take minus, so m minus 1. So if you take m is 1, it become very big problem. 1 by 0 is not a integer. If you take 2 minus 1, 2 minus 1 is 1. If you take 3 minus 1 is 2. So 3 by 2 is not a integer. So it become very big problem, depends upon the problem. So inverse does not exist, because this always does not belongs to integer. Understand? If you put only for 2, we can get inverse. Other element, it's not possible. That's all. Now Boolean matrix. In the Boolean matrix, real matrix whose entries are 0 and 1. 0 and 1s are called Boolean matrix. So that's on and off. 0 is on, 1 is on, off is 0. Like that Boolean matrix can be defined. Okay, the following kinds of operation, collection of all Boolean matrix are defined. So same type. Okay, join means operation like that, meet means like that. So now the definition for Boolean matrix, two kinds of operation, collection of all Boolean matrix. Now this is for all. So Aij, A is a Boolean matrix, Aij, Bij. So now we can get Cij. Cij 0 means Aij equal to 1 or Bij equal to 1. So if you get or this or that is 1 means 1. Both are 0 means 0. That is your definition for this join. This symbol is called join. Boolean matrix, joined Boolean matrix, or another matrix we defined what? Meet. Join matrix or meet matrix. So when you take meet matrix, both should be 1. If both Aij and Bij both are 1, then we can say this is 1. If both are 1 means. Otherwise you have to take 0, because join matrix. Boolean join means both should be 1, then only 1. So now we have two matrices A and B are given. Now we are going to talk about both Boolean matrix, join matrix, meet matrix. So they ask join matrix and meet matrix. We have to check with, here we have 0, 1. What is your A matrix? A matrix is 0, 1, 1, 1, and B matrix 1, 1, 0, 1. Now 0, 1. So this is join matrix. If either any one is, we can take 1. So here also 1, 1. Like that we can get everything is 1. Join means both should be 1. Here both is 1. So the answer is 1. Here also both is 1. So the answer is 1. If both are 1, Here a result also 1, that is meet matrix. Okay, join matrix means both are 0 means 0. So nothing is both are 0 here, so nothing is 0 here. So like that, join matrix and meet matrix we can find from the Boolean matrix. So whether Boolean matrix is closer, yes sir, it is closer operation, it is associative and identity element. 0 is the joined Boolean matrix, null matrix. Okay, it is identity matrix, identity element. 0 is the identity element, so null matrix. Null matrix is the additive, okay, for join matrix. Inverse, when you talk about inverse in the join matrix, it should be null matrix. Okay, it is impossible to find the matrix where B joined A joined B equal to B joined A equal to 0. So inverse does not exist. And meet matrix. For meet matrix 1 1 1, this is your identity matrix. But inverse not there. For meet matrix is closer, commutative, associative. Identity also, this is identity matrix, meet identity, whereas inverse not possible. Modular arithmetic. So when you talk about modular arithmetic, so we have to take divided by that and take the remainder. So that is modular arithmetic. Okay, we have to divide by n, take only remainder. So now this is additive modulo 5. So when you take additive modulo 5, so it should be multiple of 5. So there should not be more than 5. If you take 6 means we have to take 1, remainder 1. When you divide by 6 divided by 5, we can get 1. So 1 should be there. So all 5 multiples and all 0. Then all the remainders, if you get 1 remainder, all 1, 2 remainder, 3 remainder, 4 remainder. So these all called elements of additive modulo 5. Concurrency with additive modulo 5. So you have to divide by 5, take only remainder. That is another type of work. Additive modulo 5. Similarly, multiplicative modulo also there. Multiplicative modulo n also there. So now whether additive modulo is closure property, associative, commutative, this and all we have to check. Here additive modulo, okay, is additive modulo. Division we are taking only remainder. Yes sir, additive modulo, multiplicative modulo are the binary operations. We will get closure property, commutative, associative, everything we can check with additive modulo 5. When you take additive modulo 5, if you take any elements, again add becomes, suppose you take 3 plus 3, the answer is 6. But when you take additive modulo, we have to take only 1. Take only 1 because this is additive modulo. If you take additive modulo 5, by addition we have to take only remainder. So like that, 4 plus 4, it is not, 4 plus 4 is 8, divided by 5, take only remainder. So that is 3. 4 plus 4 is 3, additive modulo 5. So again by the table, this table indicates that if you add any elements in the additive modulo 5, again this element in the additive modulo 5 only. So it is a closure, it is a commutative, it is associative, and 0 is the identity element, and inverse. So inverse easily we can find. For 1, what is the inverse? 1 plus 4, we can get additive modulo 0. So 4 is the inverse for 1. For 2 plus inverse is 3. Additive modulo we can get 0. And similarly for 3, 2 is inverse, 4, 1 is inverse. So for 1, 2 inverse are 4 and 3. Okay. So it has inverse, commutative. Example 10. Now we are talking about verify additive multiplicative modulo 11. Now the question is multiplicative modulo 11. Multiplicative modulo 11 means we get only up to 10 only. If you take any values above 11, it become remainder. You take only remainder after 11. Okay, 11 multiples are all 0. So it is closure, associative, commutative, associative, identity element is 0 is additive identity, whereas here multiplication means 1 is the multiplicative identity. 1 is multiplicative. Now in that we take only subset. Verify this all the property for the subset 1, 3, 4, 5, 9. So now you take 1, 3, 4, 5, 9 only you have to take. 1, 3, 4, 5. Now multiply. 1 into 1 is 1, 1 into 3, 3, 1 into 4, 4, 1 into 5, 5, 1 into 6, 6. Like that multiply. Now this 1 into 1, 1, 3 into 1, 4 into 1, 5 into 1, 9 into 1. Everything is correct. Take 3 into 3, 9. 3 into 4. 3 4s are 12 should come. Take only remainder. 3 into 4 is 12. But this 12 you have to divide by 11. 12. What is the modulo? You take modulo 11. Then what is your remainder? 1 is the remainder. So when you multiply 3 4s are 12, take remainder 1. 3 5s are, can you tell the answer? What is the remainder? 3 5s are 15. Good. 3 5s are 15, take only remainder 4. And 3 9s are, what is that? 3 9s are 27. Divided by 11, take remainder. When you divide 22, so remainder is 5. So like that you have to multiply. Taking this table again is element of 1, 3, 4, 5, 9 only repeating. This subset is a closure. The same element only repeating. So the table you can say the binary operation on the subset A is closure, B is the associative property and identity. What is inverse? Can you tell the inverse? Yeah, 3. What is inverse? Take 3 with water, we take 3, multiply with 4 and so inverse of 3 is 3 and 4 are inverse.
Oh.
Yes, 3 and 4 inverse to each other. Like that for 5 which is the inverse? 5 into 9, 45, correct? 5 9s are 45. So we can take 1, 5, 9, 45, 44, so remaining 1. So for 5 remainder inverse is 9, and similarly for 9, 5 is the inverse. Like that, here we have completed for subset. In multiplicative modulo 11, the subset we take 1, 3, 4, 5, 9 is a binary operation, commutative property true, associative property true, 1 is the identity, and inverse. For 3, inverse is 4, and similarly for 5, 9 is the inverse.